It's a pleasure to introduce our next speaker, Andrew Chi-Chih, or Andy as he's known to his friends and colleagues. Andy got his undergraduate degree in physics from National Taiwan University, and his PhD in physics from Harvard. Luckily for us, in computer science, he shortly after that got his PhD in computer science from the University of Illinois. He's been on the faculty of MIT, Stanford, UC Berkeley, and at Princeton from 1986 to 2004. In 2004, he decided to take early retirement to go to Tsinghua University, where he's currently the dean of the Institute for Interdisciplinary Information Sciences. And due to his efforts, single-handedly, he's created a vibrant program in theoretical computer science there, firmly put computer science on Beijing on the map for computer science, and inspired the next generation of researchers from China. Andy is a member of the US and Chinese National Academies of Sciences, a member of the American Academy of Arts and Sciences. He's won many prizes in the course of his highly distinguished career. He was a winner of the George Polya Prize in '87, the Knuth Prize in '96, and he was awarded the Turing Award in 2000 for his fundamental contributions to the theory of computation. He's worked in several different areas. Some of his work in complexity-based random number generation form some of the basic building blocks for modern cryptography. He's also done fundamental work that has initiated research in communication complexity, the study of how much interaction must happen before distributed parties can compute something together. There are two kinds of mathematical scientists, those that solve hard problems and those that propose them, and Andy's work has done both of these things, solving many open problems in computer science with just sheer technical brilliance, but also conceptualizing novel ideas and showing great vision. I mentioned that Andy has won many different awards, but I hear that there's a particular certificate he received as a child that he is very proud of. This was from the local elementary school in Hong Kong, where he finished his first grade, and the first grade teacher had the following observation. Andrew is overall a good student, just a little weak in math, and should work hard at it. Obviously, Andy took that to heart, and it has served him well. And please join me in welcoming Andy up.
Thank you very much for the nice introduction, Moses. Good afternoon. It's great to be here on this joyful occasion to celebrate the centennial of Alan Turing. And I would like to thank Bob and John for organizing this fantastic conference. And today, what I'd like to talk about is quantum computing, which is a concept which has been in the magazines and news for the last 10, 15 years, both in scientific community and also in the popular press. This topic, I think it's pretty fitting for this conference because Turing machine model has been tremendously successful for the last 70 years or so. And a quantum computer is really the first serious departure from the Turing von Neumann computer architecture. And despite the many coverage of quantum computing for the last decade or so, I think to many people, even to many computer scientists, quantum computing is still somehow shrouded a little bit in mystery. And so what is quantum computing and why many find it so exciting and irresistible? And what we like to do is to shed some light on these questions. And actually, I'm not only going to argue that it is indeed a very exciting development, I'm actually going to say something much stronger. I would like to make the case that quantum computing as a discipline is a great science in the making. And now, I think it's going to be pretty difficult to define what great science is. So let's look at some examples of great science to begin with. And the first example we like to talk about is the X-ray crystallography. In 1895, Röntgen accidentally discovered X-rays, and for which that I think very soon people realized is a great discovery. And in 1901, he was awarded the first Nobel Prize in physics for it. And now, the nature of what X-ray is was, in the early days, was a controversial subject. At that time, the classical physics, you have only two kinds of objects. There are particles and there are waves. So the question is, was X-ray a particle or a wave? It was something that very much debated in the early days. Now, in 1912, Van Lau unambiguously confirmed that X-ray actually is a wave, because he demonstrated that if you shine the X-ray through a crystal, it actually shows the familiar wave-like diffraction pattern. And so now, in 1913, a father and son team, Henry Bragg and Lawrence Bragg, derived mathematical formulas to determine crystal structures, because Van Lau did was to observe that if you shine the X-ray through a crystal, it shows the diffractive pattern. But he didn't have any formula for it exactly how the diffraction pattern corresponds to the crystals. Now, the Braggs found out that you can do things the reverse way. By looking at the diffractive pattern, you can actually find out information about the crystal itself. And now in the 1920s, people became more ambitious and used this technique to determine the structures of more complicated structures like metals and inorganic molecules. And 20 years later, there are even the techniques have been refined enough that Hodgkin was able to use it to determine the structures of biological molecules. And now the Perus and Kendrew use it to determine the myoglobin structure, which is the molecule of breath. And of course, in the 1950s, the Crick, Watson, and Wilkins, Franklin, they have determined the famous double helix structure using the X-ray crystallography. And I think things got even better after that, and up to the present day, this is still probably the most important method for determining the structure of molecules. Okay, so now, in all the 9 or 10 items that I've shown, that each of them was a major advance in biology or chemistry, and each one of them won a Nobel Prize for their record. And so I think that clearly we can all agree that the X-ray crystallography is a fine example of a great science. Sorry, what's happening? Well, can somebody? Oh, I see. It's just this guy's out. Yeah. Okay. Sorry, I'll just look at this. This is.
Yeah. Look at this.
Okay. Okay. So now, the second example I'd like to discuss is, I think, it's close to many of us, namely computer science. In 1901, Hilbert. Okay, thank you. Raised the question that is it possible that one can use some sort of mechanical procedure so that one can prove theorems or discover theorems in mathematics automatically? And now, at that time, Hilbert had no doubt that the question should have a positive answer, namely that someday we would be able to do it. Now, however, in pursuing that question by many people, including the Church and Kleene, and also Turing, people stumbled upon investigating the concept of exactly what does it mean to have a mechanical procedure to carry out the computation. And the Turing invented the Turing machine model, and it turned out that this is a great computational model that is still found out to be the most general computational model that we can think of for many years. And now Turing's machine was a mathematical model, not very practical. However, in 1945, von Neumann and others started using the electronic devices to design computers, and which make the computation model, the computers, become practical. Of course, later on, Shockley, Bardeen, and Britton invented transistors, and so on. So after that, the computers get more and more powerful, and not only it has tremendous computing power, but also its application has been used everywhere, both in scientific engineering and also in the social usage. And now I think that this also is a case that computer science is unquestionably a great science. And now, what can we conclude from these two examples? Well, one thing we observe is that great science often happens when a disruptive technology enables us to explore new territories which previously would be unimaginable. And so in the X-ray crystallography case, it's the discovery of the X-ray. You can use it to probe at the structures of matter. And in the case of computer science, it's because that we have the electronic computer, which works really fast, and we can do computations predicting weathers and building airplanes previously unimaginable. Now, I'm going to show that quantum computing is a great science because it also has this characteristic. And in fact, we're going to see that quantum computing really is a confluence of the two examples that I have shown before. You have to use, essentially, you have to put the key concept of both of the two examples together. And I'm going to show you the disruptive computing paradigm for quantum computing. And so we would like to compute a function f by a Gedanken experiment, as the physicists would have it. So I like to compute a function f, and I have an input x, and I like to get the output f of x. So what I hope to do is that I can mentally grow a crystal C that is tailored for f and for x. And after I have this crystal in hand, I'm going to shine an optical wave on the crystal. And then I'm going to see some diffraction patterns. And from the diffraction pattern, I can figure out what fx is, if I'm lucky to be able to do it. And now, we're going to see that sometimes the crystal that you grow is tremendously large, so that it's just not possible to use that crystal, to build that crystal, and performing the experiment in practice. However, here is the element of computer science come in. And basically, what we would like to do is to use a quantum software simulation. So even though the Gedanken experiment, the apparatus would be exponentially large. However, if we are lucky, it's possible when we use software, we can simulate it with an exponentially speed down, so that we will be able to have something that can be done in polynomial time. And I'm going to illustrate it with a concrete problem. It's called Simon's problem in a paper written by Simon in 1994. The Simon's problem is the following. Suppose you have a black box, and this black box will turn an n-bit string input into an n-bit string output. And furthermore, this black box actually is a 2-to-1 mapping. And so only half of the 2 to the n strings are possible outputs. And furthermore, this black box is not an arbitrary 2-to-1 mapping, but actually there is a secret n-bit string S, such that the two inputs which get mapped to the same output would differ from each other just by the additive amount of the secret string S. So X plus S is the modulo 2 bitwise operation. Now, suppose you are given such a black box, and the only thing you can do is to feed an n-bit string to it and observe the output. How long does it take for you to determine the secret S? And now, it's not hard to show that if you use a classical algorithm to do it, would need exponentially many queries. Because basically, if you don't feed the black box too many strings, then the black box really look like a completely random mapping, so that you will not be able to figure out what the S is. And however, what we're going to do is to show that if you have a quantum capability, then you will be able to figure out what this S is. So let's turn to the very basic optical experiment of diffraction. So if you have a light source of a kind of with a single wavelength, a monochromatic source, and if you place a screen in front of it and piercing holes at regular intervals to it, and observe what happens on the second screen behind it, then you are going to see that the light will interfere with each other from the different holes on the first screen. And so therefore you will be able to get, when you observe the pattern on the second screen, you are going to get alternatively bright and dark spots. Okay. Now, exactly what the spacing looks like on the second screen on the wall depends upon the combination of parameters in the setup, including the wavelength of the light source and the distances between the two screens and the distances between the holes on the first screen, etc. But conceptually, what is important for us is that if we observe the pattern on the second screen, then it gives us some information about the physical setup. And now the X-ray crystallography basically is making use of this to replace the first screen by the crystal. So the crystals would serve the purpose of the first screen to make the light coming from the light source to interfere with each other on the second screen. So therefore, by observing the patterns on the second screen, you will be able to figure out something about the structure of the crystal. Okay. And now we are going to design the Gedanken experiment for our problem. Okay. And so imagine that we grow a crystal and we put the light source to it. And now the crystal is an n-dimensional cube, so that each vertex would be labeled by a n-bit binary string. So it's so it's kind of a crystal in n dimensions. And now we put a wall, a second screen, behind the crystal. And let's design a particular light propagation setup. So the light source, when it travels to a vertex X, and then from this X, how does it propagate to the second screen? Well, we require that the light source coming from X will go to the second screen so that it's exactly on a horizontal line, and that the vertical distance z is determined by the output of the black box. So if the vertex is x, and then the light is going to travel with the second coordinate equal to f of x, and now y is arbitrary. And basically we are looking at a second screen which is discrete, so that we have 2 to the n points on the x-axis and 2 to the n on the y-axis, and each one is labeled by a binary string. And now let's look at what the interference look like. If you look at the pair of x and x plus the secret s, the light coming from it would interfere with each other because they have the same f of x. So therefore, they would travel, the wave would appear at the same 2 to the n points on the axis. However, the amplitude that we have designed there will make them interfere with each other, so that, well, you can see that the amplitude is uniform. The only difference is that it could be a -1 or +1, depending on the depending on x dot y. So now you can see that the two lights at any particular coordinate y would interfere with each other depending on whether s dot y is equal to mod 2 equal to 0 or not. Okay, so you can see that it would interfere with it. And so if s dot y mod 2 equal to 0, then it means that at that point, the two amplitude would be of the same sign, and therefore the density of the light will be 4 times as large as before. On the other hand, if s dot y mod 2 is equal to 1, then the two amplitude would become 0. And so if you look at that horizontal line, then if you look at the interference from x and x plus s, then half of the points will become dark instead of the light. So the good thing is that if you observe any bright spot, it's going to give you a linear equation in S. So if you know any y, then it tells you something about S. And in principle, if you collect samples from n independent y, so if you just look at some random points, random bright points, then just observing 2n of them, then in all likelihood, you are going to have enough equations so that you be observed. You can calculate what the secret S is. So therefore, now, in principle, if you just examine a linear number of the bright spots on the second screen, you'll be able to determine S. But now, the bad thing about this Gedanken experiment is that the lattice and also the wall, the number of points is just exponentially large, so you can't construct such a physical device. Now, however, here comes the magic of quantum software. So if you think about, we don't really need to have to set up the entire device. All we need to do is just to observe a few bright spots. So you can imagine, you can dim the light of the light source. Eventually, you are going to just have one photon coming out. And so you have, all you need to do is to have a quantum computer to let you simulate the experiment one photon at a time. Each time you simulate the diffraction of one photon and observe what the bright spot is, you get one equation, s dot y equal to 0. So if you can simulate it, you just do it n or 2n times, you will get enough equations to do it. So therefore, with a quantum computer, you can simulate this experiment. You can implement it with just n plus 2n bits. You can simulate the propagation of one photon to produce a bright spot. So this way, if you have a quantum computer, then you can solve Simon's problem in a linear amount of experiment time. And this is not just a taught example, because actually Peter Shor's famous quantum factoring algorithm it's really following an approach very similar to the Simon's algorithm. So in this case, instead of S, the secret is one of the factor of n. So if you just imagine that how Peter Shor's algorithm runs, it really is also the same thing as designing a particular lattice, and you shine a wave on it, and then you simulate it with a quantum computer. And so to make the case for quantum computing, we observe that the great science often happens when the scientific theories interact and scientific disciplines interact. In this case, it's the physics and computer science, and also simultaneously when the new technology makes the concept to be possible in practice to implement it, and quantum computing is in this very happy situation. So I think the next thing you want to ask is that when are we going to see a quantum computer in place? And I think that the answer is that sooner than you think, come into a store near you. I think the common impression about quantum computers is that it's really high up in the cloud, and you will not see it anytime kind of reasonable amount of time. But actually, if you talk to people who work in this field, people are much more optimistic about it. I think that the impression about the remoteness of quantum computing probably was due to the skepticism in the early days, let's say that 20 years ago or 15 years ago. I think there were tremendous obstacles to it, both in principle and in practice. But actually, if you look at what people have done in the last 20 years, I think that the progress is really much faster than people could have imagined in the beginning. If you don't believe it, I think that one evidence is that a lot of countries are putting a tremendous amount of resources into building quantum computing devices. I think that the fact is, I mean, I'm not a hardware person, but I think that basically the people who are building, making progress toward quantum computers, they all like to tone down the rhetoric. They all want to keep a low profile. So actually, this is a case that is very different from many other subjects. So actually, I think that things are progressing much faster than one would have guessed. And so you can see that in many countries in the United States, I think the NIST Maryland has probably the largest quantum information lab, and with 30 professors working in it, and the Harvard MIT has a Center for Ultra Cold Atoms with 15 professors working in it, and now even Microsoft has a branch in Santa Barbara that works in quantum computer, and as you can see that there are famous people, Nobel laureates and the field medalists working in it, and in Canada, the University of Waterloo and the Perimeter Institute, I think they have a very big setup for building, I think, the most advanced possible future solid-state quantum computer, I think using superconductors for doing it. In Singapore, there's a very big national center, and also there are other centers in Europe, Japan, and in China. And actually, at Tsinghua University, where I work, we have started since last year a project in building quantum networks. And now the rationale is the following. Internet is now an indispensable part of modern society, and so you can send messages from any place to another place. Now, what about the building an advanced version of internet? Namely, how about building a quantum internet so that we'll be able, in the ideal case, to send not just classical strings, but actually quantum signals from any place to another place. Is it possible to build quantum networks? And now, building quantum network, it's if you want to at some point realize quantum communication and computation, you need to build quantum networks. Now, nowadays, the typical quantum communication that you can send by using the fiber optic, it's limited to let's say 15 kilometers. In order to get it to longer distance, you have to build quantum repeater network in order to do it. It's a very sophisticated concept because I think there are a lot of very severe constraints on quantum theory, so that it's not just like amplified and repeat in the classical case. But people have found very clever ways for doing it. And now, actually, there's another rationale for building quantum networks, namely that people have realized that building scalable quantum computers, one way to do it is to build quantum networks so that you only have to build very small quantum computing nodes, let's say 10 or 15 quantum bits, and you can connect them together by a quantum network. And so it really is the same paradigm as we do for building supercomputers. And now there are different technologies for building quantum computers and quantum networks, and the trap ion is probably the most mature technology. And so if you use, for example, trap ions, it's possible to build expandable quantum computational network. So all this, the theory is already here, and I think people have worked out the entire theory, and now it's waiting for the physicists to realize them. And so the vision is you have the quantum registers, and they are connected by the optical fibers and interact with each other. And now, building quantum computers essentially is trying to you take apart a classical quantum network, and if you take a typical classical network or classical computer, and you just repeat component by component. You build small computational node, and then you work out the interface between the cables and the computational node, and so on. And the difference is that in the quantum case, every step is a big effort. So every step, you have to do a lot of new experimental work for doing it. And there have been a lot of work on it, and as if you just take the top scientific magazines like Science and Nature, that every few issues you will see progress made. So, for example, you would work on the entanglement and the interface between a quantum material bit and a quantum message bit. So that would, you have to do serious physics in order to do it. And you might want to just directly entangle and do computation with the material quantum bits. Okay. So things are progressing very fast. And now, to conclude, I want to reiterate that great science often happens when scientific theories interact and scientific discipline interact, and also when new technology becomes available to make it happen. And quantum computing is in this very happy situations. But to end the talk, let me come back to to the beginning when I say that it's very hard to define what great science is. So therefore, I try to argue by showing you some examples, and then by arguing that quantum by the pedigree argument that it is a product of two great sciences. And let me come back to the beginning. Exactly what is great science? And I think that this really is a subjective question. However, I think that two requirements are probably we all can agree upon. The first is it must have deep impact. I think that I personally think that it should have impact beyond just intellectual curiosity. And is there, so in the quantum computing case, if we can build quantum computers or actually on the way to building full-scale quantum computers, it is possible to think about performing quantum simulations. And this can help us to design new materials and also test physics theory. For example, in physics theories, I think that the room temperature superconductors have been around for a while. Now, not quite room temperature, but a relatively high temperature, but people don't know exactly what is the theory behind it. So there are different theories to explain this, competing theories. Now, we have the mathematical formalism, but we don't know how to deduce conclusions from it. We cannot calculate it. And classical computers are not powerful enough for us to simulate the quantum theories. However, if we have quantum computers or something just along that road, then it may be possible to use it to derive, to simulate, to get consequences of the theories and therefore can tell these theories apart. So, and now, the second requirement, I think that in addition, it should uplift the human spirit. And I think in this regard, quantum computer and in general, quantum information processing has a lot to contribute. And basically, we have known that the world is quantum mechanical and not classical for over 100 years. And so basically, we know the equations and we know how, in principle, it works. However, it's only in the last 20 or 30 years that that human beings are beginning to be able to actually develop quantum technology to a state where one can actually control it. And in particular, even with today's optical fiber, it's possible to send one photon at a time down the, and therefore it's truly quantum signals. And now, this is something that is remarkable because I think in the many millions of years where the life has occurred, or lives that are capable of communicating, that we have always been using classical communication. In principle, it's just between Alice and Bob, and we have binary strings going back and forth all the time. However, now we can send quantum signals. And so this is the first time we can talk in a quantum language. And in principle, it should be possible to have a much different type of interaction. And now quantum computing this allows human beings to communicate with quantum signals. But at a deeper level, especially when you think about quantum computers, we are really trying to communicate to a very different community. We think about the subatomic particles community, which have a language, the quantum language, all of their own. So it's just like there's a tribe that lives on a certain island somewhere in the Pacific, and we understand their language, the quantum physics language. However, we have never been able to get there, and we can communicate and talk to them in that. But now we are getting to a point that it's possible for us to actually go there, and we can use their language to converse with them. In this case, these subatomic particles happen to have a great power over our ability, namely that they can do quantum computations in a way that, for example, factoring large numbers. So right now, we know that our goal is to be able to develop the quantum technology to a state where we can explain to the natives that now here's a pattern of delicate dance. Can you just do the dance for me? And if we can succeed in doing that, then this tribe would line up on the beach and perform the integrated dance that we would never be able to imagine or do. And at the end of it, they will leave prints, they will leave numbers on the sand of the beach, and they spell out what the prime factors are for the large integers. And so I rest my case. Thank you very much.
Wait until we have someone on the mic come up. Who has the mic?
Thank you very much for your talk, first of all. What are the implications of quantum computing in current cryptography mechanisms? If such a machine was built, would that mean that the core practical security principles on which current cryptography mechanisms are based would be called into question?
Yes, I think that currently The most talked about quantum information processing applications is the security applications. So it goes both ways. Firstly, if you can build quantum computers, then it's going to crack a lot of the codes, which we currently thought to be the most secure codes. And secondly, it also has a positive effect, namely that quantum cryptography enables us to build codes which in principle would be a lot more secure than any classical codes, because you have to invalidate quantum mechanics in order to be able to break these secret codes. So that's the I think that's the most obvious applications of quantum information processing. And however, I think that scientifically the most important one is the one that I mentioned, that when you do quantum simulation, you'll be able to simulate quantum theories, which we're not able to do. For example, in chemistry, I think one of the grand challenge problem is to be able to solve the Schrödinger equation for a system with, let's say, 100 or 200 electrons. And so for even moderately sized molecule, currently the classical computer will not have enough computing power in order to solve for the eigenvalues for the Schrödinger equation. But if you have quantum computers, we should be able to do that in a flash.
So Andy, this was a fascinating talk. It seems like in quantum computing, the hardware is way ahead of the software. Okay, we know how to build, I mean, we know some physics as to how to build the hardware. But if you take the analogy with computers, today, if we try to get software people to understand transistors, the language of transistors and the hardware aspects of which modern electronic computers are built, we won't get very far. You see, so what the question I'm asking is, what are the most appropriate quantum software programming paradigms? Because even when we got to like machine language and assembly language, we won't get very far if everyone had to program today's digital computers that way. But the programming paradigm today is closer to the problems you want to solve that humans understand. And so to express the correct quantum software programming paradigm, we need to, what do you think this would be like? We need to understand the nature of the computations that can be done.
Yeah, I think that as soon as the quantum hardware technology seems to be right around the corner, there will be people who will build quantum software for running it. Actually, there are already people who have embarked on it. And last year, I went to a conference in Saudi Arabia. I think Les Valiant was also there, and I planned to give a quantum talk there. And I worry that it's too far ahead of the time. However, I saw Al Aho there, and who gave a talk on quantum compilers. So actually, that immediately put my mind to ease. And so Al talked about actually his work at Columbia on how to do it. And so I think that if we really have a big quantum computers available, then I think we have to redevelop everything. We have to design compilers. We have to design operating systems. We have to so in principle, if everything works out perfectly, then we will have a lot more work to do in computer science. But I think that we probably don't have to worry about it for a few years.
I just want to follow up on the previous question. Conceptually, how should we think about the quantum computing? Is it like, do we think about it like very fast analog devices that are very specialized? Or are we talking about a Turing machine, a sort of a universal computer? In other words, is it a series of different specialized techniques that will solve a specific problem, and we have a fast quantum computer that does A and a fast quantum computer that does B and C and so forth, and we just link them together? Or do we have something that is a general purpose processing machine that one machine will solve whatever problem we give it?
Well, initially, we expect that we're going to see specialized machines. For example, machines that are dedicated for breaking RSA codes. And but in principle, one can construct universal quantum Turing machines that would execute quantum software programs. And I mean, there's no conceptual difficulty in doing that. And so I think that in principle, I think that I mean, all the complexities and all the necessary components of the classical computing theory and practice, I think they are also available in the quantum version.
Do you think that quantum entanglement will lead to unexpected phenomenon?
I think quantum entanglement certainly already have unexpected consequences. I think that in the very early days, the Bell inequalities, and which in the modern rendition, it's really can saying that if you participate in the game show, and if two parties who before the game show they establish some entanglement, then they can come out really look like wonders compared to other people, and I think that they would be mistaken as being they have the parapsychological abilities, and so I mean, are there really huge unexpected? I think that right now I think that we know all the mathematics, and whether one can work out some even more fantastic demonstration of the power of entanglement. I think I think theoretically we already have a very interesting examples in the mathematical sense, but I think could we have consequences like we can send bits, have a killer applications such as that we can send a tremendous amount of information with a very small device and the cables. I think that kind of killer applications, we have not seen it yet.
So I think currently we're up to about 6 qubits. Do you have some notion of how many qubits we'll need before we're actually doing practical computations that we're doing, not just to demonstrate because we want the answer and the quantum machine can get it faster? How big will it need to be? What do you think the first applications will be? And would you hazard a guess as to how long it will be before this happens, other than sooner than we think?
The most leading technology right now is the ion trap technology. So you have ions. So you have the atoms. You take away 1 or 2 electrons, and then this is an ion, and you can line up those ions together in a dynamic magnetic field, electric field, so that they can form a linear array of quantum bits. And right now, I think that the record is 14 quantum bits, and on which they can demonstrate entanglement. And I don't think they have the absolute control over the interactions between any two of the bits yet. But I think that kind of a dozen quantum bits in the iron trap technology, I think it should be doable within the next few years. And now, as I said, that well, if you have those as basic unit, and then you can connect them with quantum networks, then you can get to have some computing capabilities. But I mean, you have a lot of things that one has to worry about. The error correction, in principle, can be done, but nobody has actually done it yet. And so there's a lot of research that needs to be done. And of course, I think that people are working on the physicists are working on many different fronts. I mean, one front is to take this leading technology to as far as it can go. And there are also people who are working on new generations of technology. For example, the solid state the quantum computers, because those would be, if you want to manufacture in a large scale, and also if you want to carry them to become portable, then right now I think that the superconducting, use superconducting material to do storage. I think that right now they can do 3 quantum bits on it. And then there's the one that using diamonds with defects. And that's even better, because the diamonds, you can do it at room temperature. So you don't. So if that develops, then it will be the ideal medium. So all these are progressing, and we don't know the schedule. I think the physicists they don't want to talk about it. I mean, it's amazing that they say that they want to avoid the words quantum computers in the publicity as much as they can. I mean, they just don't want to create over expectation of their work. So I don't know exactly, but I imagine that it's going. It would go faster than you think. I think in 10 years, I think that we will not be, talking about whether it can be done, but we'll be talking about, when to form a company.
I know there were more questions in the audience, but I think that time will stop the session here, and I encourage you to approach Andy in the break. Andrew Appel has an announcement for us before we break.
All right, well, let's first thank Andy again for a great talk.